here is that when light rays travel different distances, that they get out of phase, right? So, for example, if I have, and I'm going to do an easier question first, and then I'll go to the mountain question, okay? If I have two waves, one wave right here, and this wave has a wavelength, say, of 2 meters. That's my wavelength. From this point to this point is one wavelength. And then let's say that after this wave goes, another wave that's been traveling a longer distance, it arrives so that it is, say, 1 meter offset. So if I go 1 meter offset, which is right about there, this new wave will start and look like this. So here I have a path length difference. I'm going to call it PD. It's just the change in the different distances that the two waves traveled. That's equal to 1 meter. And 1 meter, right, that's just, that's this distance. 1 meter is equal to half a wavelength. And because of that, that path length difference is equal to half a wavelength, I get destructive interference. Right. Now, the mountain problem that we saw, you had a mountain, and then you had over here a radio tower, so it's putting out these waves. That's our radio tower. And then you have a house right here, and it's picking up these waves. So it has an antenna out here to pick up the waves. And I have two waves that come. I have a wave that comes straight to the house, and then I have another wave that goes from the antenna, and then it reflects off of the mountain, and it comes there. So this second wave has a longer distance to travel, and what's important is the path length difference will tell you whether or not you have constructive or destructive interference. So I want to know, what is this extra distance that it's traveled? I'll call this X. So I'll call that X. And then whatever that extra distance is, twice that is how much my wave is now out of phase. Follow me? So the important thing is this path length difference, and then what integer of wavelengths. So let's say that these radio waves have a wavelength of 100 meters. They have a wavelength of 100 meters, and let's say that this distance is 50 meters. Then that means that the waves, the purple waves here, are going to travel an extra 100 meters. Because they travel up to this point, and then they go another 50 meters, and then another 50 meters. So they travel an extra 100 meters. That means that the path length difference is 100 meters. And that's equal to 1 wavelength. Because it's equal to 1 wavelength, I have constructive interference. You will see several questions about this, at least 2 questions. I'm not saying you see the mountain problem in particular, but you'll need to know this idea of path length difference, and when that path length difference is equal to either an integer value of wavelengths, 1 wavelength, 2 wavelengths, 3 wavelengths, and on, then you're going to get constructive interference. And when it's equal to a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, and on, you get destructive interference. It's very important for our double slit experiment, because that's the idea behind it. Okay? Does that help a little bit? Okay. Any other particular questions? Or I want to know, like, sort of a recap of everything. Okay, that's fine. How about you, ladies? Anything in particular? Okay, that's the opposite structure. It's about equal, by the way. Recap also? All right. Yeah, so lots of big topics in chapter 7. The way I break it up is I think of mirrors, of course, and within mirrors we have ray tracing. All right. You will have one question where I just give you a mirror and I ask you which one of these rays is correct or incorrect. All right. I'll give you a series of rays that I've drawn on a mirror, and you'll have to pick out which one is correct or incorrect. So say, for example, I have this concave mirror. This is my object, and I would draw several rays. All right, I'll draw this one. It would go like that. I could draw, let's see, I'll call this the center of curvature right here. I could draw one that goes like this, and I could draw another one that looks like, I don't know, like that. All right. This one would be the incorrect ray. So you just need to go back and make sure you know those rules for drawing the rays, because those will be 2 questions. But it's also very important that you know what type of mirror produce what type of images, because that comes up in some of the word problems. And I also just give you some questions. What type of mirror produces this image? What type of mirror produces this image? And with mirrors, we have basically 2 types of mirrors. We have our concave mirror, and then we have our convex mirror. Remember, a concave mirror, that's like a shaving mirror or a makeup mirror. All right, and a convex mirror, this is like a security mirror. For the concave, we have 3 different scenarios. Right? If your object is outside the focal point, this is my object, that means that your image is real, inverted, and it can either be magnified or not. So it's real and inverted. If my image is at the focal point, like this, my object rather, there's no image at all. And if my object is inside the focal point, this is my object, my image is right here. This image is virtual, upright, obviously, and it's bigger. All right, so you need to know those different types of images. So, for example, I might give you a problem where I say this is a mirror, this is my object, and my image looks like this. All right, and I ask you what type of mirror or lens is this? And you say, well, that has to be a concave mirror because it's a bigger virtual upright image. All right. For convex mirrors, they're a little simpler. This is a convex mirror. The focal point is back there. The image is always upright, virtual, and smaller. We went through those in the notes, but you'll need to know those. Like you'll just ask some explicit questions, a couple of questions, where I just ask you what type of image is formed by this thing, or I give you this sort of mystery device with the image, and you tell me what the device is, whether it's a concave, convex, lens, or mirror. Okay? So you can tell the difference between them in that way. Know what types, and then also in some of the word problems, you'll need to know from the numbers that I give you and the type of image that's being formed, how or what type of mirror or lens is being used. All right, so for example, if I give you a problem and I tell you that the image is bigger and it's upright, then you know that it has to be a concave mirror because there's no other mirror up here that gives a bigger upright image. It has to be a concave mirror, and then that would be important because, well, the image distance would be negative. So like I might give you the distance from the image, but I'm never going to give you a sign. There'll be no signs at all. So you'll need to know what are all the various signs. So for example, if I give you the image distance for this scenario, you'll need to know that it's negative. I would sketch out the thing. That always helps me when you're working upon to sketch out the mirror and where the object in the image is. Also, you need to know this has a positive focal length, whereas the convex mirror has a negative focal length. A good way to remember that is just always look for where the focal point is. If it's on the back side of the mirror, that means that's like the negative space on the back side of the mirror. So this focal point is negative. This focal point, which is on the front side of the mirror where the object is a positive focal point. Right, so concave mirrors have a positive focal point, convex mirrors have a negative focal point. You'll also have some problems, and we have time, we can look at some problems, word problems. We're just using these equations, 1 over f equals 1 over p plus 1 over q. And m is equal to negative q over p. You will have a substitution problem, and you had a substitution problem where you had to solve this system of equations, on your homework, and you can find some in the old test. But one, for example, where you would know the magnification, say the magnification is equal to, I don't know, -2. Can it be -2? No, +2. Say the magnification is +2, and I give you the focal point, and I say the focal point is 10, and then I ask you for, I don't know, Q or whatever. All right, the way that you would solve that is you would say that Q is equal to -m times P. Just solving this for Q. I'm sorry. Let's say I'm looking for P. I'm looking for P. There are problems like this in the homework and as well as on old tests, but you would say Q is equal to -MP, and then you would take this and you'd plug it in for Q. And then you can solve that because you would have an equation 1 over 10 equals 1 over P plus 1 over -2P, because I know that my magnification. And then you can go ahead and solve that for P. I try to give you really easy numbers. There are no decimal numbers as far as using the lens or mirror equation. So you should be able to do it without your calculator. It's easier if you're able to do that through the fractions without doing a calculator. But if you're not able to do that, that's fine. But you should be able to solve something like this for P. Can you do that? Solve this for P? Maybe? Yeah. Like, the way I do this, you have to find a common denominator. So you'd say 2 over 2P minus 1 over 2P. And so this would be equal to 1 over 2P. That's equal to 1 over 10. So P is equal to 5. Cross multiply 2 pi at 2P is equal to 10. P would be equal to 5. You will have a problem, something similar to that. When we're done, we can go back and look at some old tests. I'll show you an example. Now, for lenses, very similar. You need to know your ray diagrams, and you'll have a problem where I give you some rays, and I'll ask you which one is the incorrect ray. There's some in the old test. There are some similar problems to that, but just knowing those ray diagrams will help. Also, just knowing for the lenses the different scenarios that you have. These are 2 different lenses. This one is convex, and by the way, this is a converging device. That means, the light rays converge when they go through it. This is a concave lens, and this is a diverging device. Don't forget that these have different names than the mirrors. So the convex lens acts a lot like a concave mirror. That's because the concave mirror is also a converging device, and the convex. So the convex lens and the concave mirror are a lot the same. The concave lens and the convex mirror are also very similar because they're both diverging. All right, so you need to know that where the types of images are formed. Oh, by the way, convex has a positive focal point. This has a negative focal point. Be careful, the names are switched, okay? Because a concave mirror has a positive focal point. A convex mirror has a negative focal point, so they're switched. All right, so here I have 3 scenarios. If my object is here, my image is over here. This is a real inverted image. If my object is at the focal point, that's no image at all. You should know the rays for these, because I'll give you one of these scenarios and ask you for the rays. If my object is inside the focal point, that means that the image is right here. This is a virtual, upright, bigger image. This last one's like a magnifying glass. You look at something in a magnifying glass, it always appears bigger, it always appears upright. That is a virtual image. The virtual image with the lenses, a virtual image is always on the same side as the object. Right? Virtual image is always on the same side as the object. That's different from mirrors. For mirrors, the virtual image is always on the opposite side from the object. For this, the concave lens, if my object is here, my image is here. This image, just like the convex mirror, all right, it's a virtual, upright, smaller. So if you look back and you compare this with what we had for mirrors, it's exactly the same. Alright, except over here with the mirrors, we had concave mirrors, and here we had convex mirrors. So it's exactly the same, or largely the same, in the types. It's exactly the same in the types of images that it forms. It's a little bit different, whereas with the convex mirror, which is like the lens, the image was on the other side, on the back side of the mirror. That's just the way it is. For lenses, the image, virtual images are on the same side as the object. Real images are on the opposite side of the object. It's not that way for mirrors. It's different for mirrors. Okay, so a lot of similarities, but also some subtle differences. And then similarly with this, you'll need to apply the lens equation 1 over f equals 1 over q plus 1 over p. All right, you'll only have, and then also the magnification, negative q over p. You'll only have one of those where you have to substitute that one equation into the other. Okay, this just sort of takes a little bit of time. But you will have to do some simpler calculations for the lenses. All right, I give you q and p or whatever, and you have to find f. Or I give you f and q, and you have to find the magnification. So for example, if I gave you f and q, you would first have to solve for p, and then you would have to take that value for p and solve for the magnification. So you will have a problem like that. And there are lots of examples like that. We can look at them if you like. Okay, and then you'll also have one two-lens problem. Two-lens problem looks like this. It'll be two convex lenses. They'll be separated by a certain distance. I'll tell you that distance. We'll call it x here. I'll show you their focal point, so you'll know f1, say 10 centimeters, for example. f2, say 20 centimeters, for example. And then I'll tell you what is this object distance. So I'll call this P1. Right, you'll first calculate Q1. So Q1 will be something like this. And then you find this distance. This is going to be x minus Q1. And this is going to equal P2. We can look at an example like this a little bit later. But basically, this image becomes the object for this lens. We worked through problems like this. I think last week we worked through these. All right, so this image becomes the object for this lens, and then it produces another image. You can calculate the magnification. All right, yeah, so we'll get another image out here, and this will be located at distance Q2. Calculate our magnifications, negative Q1 over P1. M2 is negative Q2 over P2. And then if you want to know the total magnification, it's equal to M1, M2. You will have a two-lens problem. It will not be, I don't know if we've talked about this, but it will not be one of those where you're dealing with a virtual object. That's where the lenses are really close together, and the first image will be on the opposite side of this lens. It's going to work, it'll be just like this. All right, just remember to put it into it. All right, I'll either ask you for the total magnification, or I'll ask you for the position of the final image. One of those. Just one question like that. And you also, in this section, we had aberrations. We had spherical aberrations, and we had chromatic aberrations. Spherical aberrations are caused by the spherical shape of the lens or mirror. You need to know, for these aberrations, you need to know what causes it, what it affects, and what you do to get rid of it. Spherical aberrations are caused by the spherical shape of the lens or mirror. It affects both the lenses and mirrors. And the way that you get rid of this is you either add an aperture, or you use a parabolic mirror, if you're talking about mirrors. All right, so that's spherical aberrations. There's also chromatic aberrations. I'll make it up here for a second. Chromatic aberrations are due to the wavelength dependence of the index of refraction. Can I go down? Yeah. All right, so chromatic aberrations. Chromatic means color, so that's can help you remember that. Chromatic aberrations, because the index of refraction, if I were to plot n versus lambda, it looks like that. Chromatic aberrations only affect lenses. The reason is that mirrors don't exhibit refraction, so the index of refraction is not important. It's due to the wavelength dependence of n. That is, n varies with wavelength. So blue light, for example, would bend more than red light. The way you get rid of this is you just have to use a system of lenses. I wouldn't ask you how to get rid of this, but you have to use a system of lenses to mitigate it, to sort of minimize it. But know what it's due to and what it affects. It only affects lenses because mirrors don't refract light. They only reflect light. Okay, I think that might be it for that chapter. Let me just do a quick check. Can I go through chapter 8 as well? Recap. As you know, a good way to practice this is to look through the old tests. I would practice the old tests just sort of on your own, and then you can go back and look at the solutions. Yeah, that's it on this chapter. Let's look at chapter 8. Chapter 8 falls into several different categories. We're going to look at interference, the double slit experiment, the single slit experiment, and diffraction grating. So those 4 topics, as well as the trial question about Fraunhofer. That's the circular diffraction. I'll show you that makes this really easy. All right. So interference. You need to know about waves when they're out of phase. If I have 2 waves that are like this, did we talk about this last week? Interference and all that? No? Okay. Good. All right, so if I have 2 waves that are like this, when the peaks line up with the peaks and the troughs line up with the troughs, you get a wave. When you add those together, if I add these together, I get a wave that just has a bigger amplitude. It's like water waves. When water waves come together, the peaks line up with the peaks, you just get a bigger wave. The same is true for light. We call these waves in phase. You will have a couple of questions just asking you to identify waves and whether they're in phase or out of phase. Right. If I have, on the other hand, 2 waves look like this, right, we call these, if you add these together, you get nothing at all. This occurs in mechanical waves, like on the ocean as well. If you have 2 waves that are out of phase and they come together, the water goes still. This is called out of phase. We have a couple of different terms to talk about this. It is either a wavelength over a half a wavelength out of phase, or 180 degrees out of phase. You can be asked to define either. So if I have 2 waves that exhibit this destructive interference, this is called destructive, this is called constructive. Destructive interference, they're out of phase. They're out of phase either by a wavelength over 1/2 a wavelength, excuse me, or 180 degrees. We have some in-betweens as well. I'll only ask you to do 90 degrees out of phase if they're offset by a 1/4 wavelength. So if I have 1 wave right here, right, this is a wavelength, that's 1 wavelength, and so a 1/4 wavelength is about right here. That means that the next wave would start right here. All right, so the peaks don't line up with the peaks, and the troughs don't line up with the troughs, but you know, it's somewhere in between. This is a 1/4 wavelength out of phase, so I would say that these are either 1/4 wavelength or 90 degrees out of phase. You'll have to identify 1 or more of those. When 2 waves when they come together, they're either going to experience total constructive interference. Total constructive interference occurs when they're in phase, or we're going to have that go through a second. Or they'll be a half a wavelength out of phase. We also call that 180 degrees. That's total destructive interference. Or something in between, which is neither constructive nor destructive interference, but it's some combination of it. So if I add these things together, I'm just going to get a really funky waveform. Okay, because the way they add up is not clean like the other 2. You need to know these terms: 1/4 and 90 degrees, half and 180 degrees. Right, these things come about because you have waves that travel different distances. So we were talking about earlier, I have this wave that travels a certain distance, and then if I have another wave that comes along and it picks up right here, because it gets a later start, this is one wavelength, if it gets a later start, because it's been traveling a longer distance or whatever, or it's delayed for some reason, if it's delayed by one wavelength, then that means I'm going to get constructive or destructive interference here. The peaks line up with the peaks, and the troughs line up with the troughs. Constructive is right. Destructive means it's destroyed. Constructive means that you construct a new wave with a bigger amplitude. Alright, so here if I'm offset by a wavelength, my path length difference, this is my path length difference. If it's equal to a half a wavelength, I get constructive interference. If it's equal to, I'm sorry, did I say half? If it's equal to one wavelength, I get constructive. If it's equal to a half a wavelength, I get destructive. So here, if my light ray, notice that the peaks line up with the troughs, and the troughs with the peaks. I'm looking at the blue wave up here up top. Sorry, it's a little confusing. If I have this wave combining with this wave, which has been offset by half a wavelength, these two are going to destruct one another. Destructive interference. They'll destroy one another. Because I have this phase shift, it's out of phase by a half a wavelength. This one was out of phase by one wavelength. This is also true for this one at 1/2 wavelength path length difference, 1.5 wavelengths, 2.5, 3.5, 4.5, and on and on. Here, 1 wavelength, 2 wavelengths, 3 wavelengths. That's where our order numbers come from for the double slit. So this segues into the double slit experiment.
Written down, I have total constructive interference occurs when they are totally out of phase.
No, that's not true. When they're totally in phase is when total constructive interference occurs. Or when they're out of phase by 180 degrees. But no, not 180. No. I'll write that down. Total constructive interference occurs when they're in phase. There is a way to talk about it as well, being out of phase by 360 degrees, but that's the same thing. So we don't talk about it. All right? So remember, this half wavelength was also out of phase by 180. Okay, we have some problems in the quiz where, for example, you have two waves, say a wavelength is equal to 2 meters, right? And these waves, wave 1 travels, I don't know, 5 meters, and wave 2 travels 3 meters before they combine, and it asks what happens. Do you have constructive or destructive interference? The key thing here is the difference in these path lengths. 5 minus 3 is equal to 2, and because you're going to be offset by 1 full wavelength, that means you'll get constructive interference. Alright, so wave number 2 gets there first because it travels a shorter distance, but then wave number 1 gets there last because this path length difference, 5 minus 3 is equal to 2, and that's equal to 1 wavelength because the wavelength is 2 meters. Or it could some be integer values. So like if this was equal to 4, that would be 2 wavelengths, and you would still get constructive interference. I had some questions like that on an old test, and you'll see something similar to that on the test one there. Alright, so that's interference. This is related to the double slit experiment, because with the double slit experiment, it's a very nice experiment where it showed that you have these slits, or you have these waves that are combining. I have one wave that travels, say, from here to here. I have a bright spot, and I have another wave that travels from here to here, and they have a slightly different path length difference. That's my path difference. And when that path length difference is equal to an integer value of the wavelengths, I get a bright spot. So see the red squiggly line? that it represents the intensity of the light. So in the middle, where the intensity is really far to the left, that means that it's really bright. So this is my brightest spot right here. Here the intensity is 0, so it's a dark spot, bright spot, dark spot, bright spot, dark spot. Here I have a bright spot, and it's the path length difference then. This is 0 path length difference. This is 1 wavelength. This is 2 wavelengths. So it starts at 0, 1 wavelength, 2 wavelengths, 0. This is a half a wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths, 2.5 wavelengths. See the half wavelength intervals, I get a dark spot because that's destructive interference. Okay, so here, this is my second order, m equal 2 we call it, and the path length difference here is equal to 2 wavelengths. That means that this wave traveled 2 wavelengths extra to get to that point. The expression for this is d sine theta equals m lambda. You'll have, I think there's one calculation for this, that you'll repeat it for diffraction grating because it's very similar, or you have a similar calculation. Just where you either have to find one of these variables, I give you 3 and you have to find one of the others, or you might also have to find, you shall have to find the distance from the central fringe to one of the other fringes. It's really simple, because once you say, I give you m, lambda, and d, if I give you these 3, you solve for theta. There's some homework problems where you have to do this. And then you find the distance from here to here. I'll call this y. Now notice this is a triangle. I have a triangle here. This is my angle theta. I'll call this L. Alright, so tan of theta is equal to y over L. Some variant, I think, of that is on your equation sheet. And then you would solve, once you find theta, I would give you L and you would solve for y. And this is the distance from the central fringe to whatever fringe it is that you're dealing with. This expression, this is on your equation sheet, but don't forget too that the order numbers are 0, 1, 2, 3, and on and on. Alright, so you will have a calculation like that. Again, there's some homework problems to help you with that. And if we have time, I can show you some problems. You'll also have single slit. Single slit works very similarly, but the equation is a little bit different, so you have to be careful. You'll only have one single slit problem. It might not even be a calculation. It might just be sort of one of these. If you change this variable, what happens to the other things? You get a very similar pattern. It looks a little bit different, but you have this idea of a central bright fringe or a central bright spot that's really bright, surrounded by increasingly dimmer spots. All right, so this is my single slit. This distance is the width of the slit, and a sine theta is equal to m lambda. But be careful because this is for dark spots. The previous one was for bright spots. This was for dark spots. So I would call this my first order. This dark spot is m equal 1. This dark spot is m equal 2. Down here, m equal 1, m equal 2. And on, m equal 3, 4, and 5 until it ends. Alright, so for example, we had some of this on the concept test. What if I said, how can I make this interference pattern broader? How can I make this get bigger, get wider, the central bright spot? To make that get bigger, what I'm saying is this theta has to get bigger. So if I wanted theta to get bigger, I could do a couple of things. I can make A smaller. If I make that slit width smaller, this pattern spreads out. So I can make A smaller, or I could increase lambda, and that would also make the pattern get bigger. So if I want theta to get bigger, that means the bright spot spreads out. I would either have to make A smaller or lambda bigger. We had something like that in the concept test, the quiz that's due today. You'll see some questions like that on it. if I change one variable, what happens to the other? Also, be careful, and there are some questions on that quiz as well. If I change one variable, what happens to this distance? All right? And remember, that distance is equal to y equal L tan theta. So, for example, let's say, what happens if A goes down? If I make A go down, that means theta goes up. If theta goes up, that means y goes up. We've already said that, right? That if theta goes up, it gets broader, it's spread apart more. But I could ask you something more along the lines of that as well. You will have more than one question related to that. If I change one variable, how much does it affect the other variables? Okay? Right, so practice problems on the concept tests due tomorrow. There's OP quizzes. All right, that's single slit. I think you just have one problem with single slits. So, but that's one problem you don't want to give up. And then diffraction gratings are the last major topic. Diffraction gratings, a couple different things. These work exactly like double slit. That is d sine theta equals m lambda, where m equals 0, 1, 2, 3, 9, and 9, with a couple differences. One is how we measure d. A diffraction grating is just a piece of plastic. It's about the size of a film slide, depending on what you're using. But it has a bunch of different grooves on it. I had a little sketch of one. And usually we give it in terms of this. Like we would say this one would have 1,000 lines per centimeter or whatever. In order to find d, this is not d. d is actually equal to 1 over this value. You will have a problem where I just give you this diffraction grating has blank lines per centimeter or millimeter. What is the distance between the slits? And this is how you'll do it. So the distance is just the inverse of that number in centimeters. So you notice lines per centimeter, centimeters per line if I invert it. So that tells me how many centimeters between each line. I'll ask for it in SI units. So this is going to be 0.001 centimeters, which is 0.00001 meters. It'll really help you if you remember your metric prefixes first. Remember, centimeters is 10 to the minus 2, millimeters is 10 to the minus 3, nanometers is 10 to the minus 9. But it'll also help you, like I just did here, you can just do this in your head and move this from 0.001 centimeters to 0.00001 meters. Just move it over 2 decimal places to the left. Okay? That'll help you so you're not fiddling around with units. But you will have to do some unit conversions for all three of these. Because whenever you're doing diffraction gratings, this wasn't true for lenses, but whenever you're doing diffraction gratings, single slit or double slit diffraction, you always have to be in SI units. Alright? Okay, so that's diffraction gratings. And then you'll also have some problems like we had with double slit, just applying this. But everything's the same. D sine theta equals m lambda, and y equals L tan theta, if you want to know the distance between the spots. And then one other thing that's regarding double slit, single slit, and diffraction gratings is the maximum number of orders. That just means the maximum number of bright spots you have on a screen. So for example, here's my screen with bright and dark spots on it. We'll do it for double slit. Imagine this is the angle theta. The maximum number of orders occurs when theta equals 90 degrees. So if I ask you what is the maximum angle or what is the maximum number of orders or others, you just say, well, theta equals 90 degrees, and you solve for m. There are some old test problems like that. I think there's some on the quiz as well. Just asking what is the maximum number of orders. And so for example, if I had my double slit here, and I was asked what is the maximum n, I just say d sine theta equals m lambda. And I would just say sine of theta, sine of 90, that's 1. So d is equal to m lambda. So m is equal to d over lambda. And then that would tell me some number, and that would be my maximum number of orders. So for example, if this worked out to be 3.15, then I would only have 3 orders. I would have 1, 2, and then I have another one out here, 1, 2, and another one out here. There's a homework problem, or very, very last thing, and you will have a problem like this. There was a picture in your book. I'm not going to be able to recreate it very well, but if you shine a bright light onto a circular aperture, you can do it. Like you take a penny and you shine a bright light on it. You don't just get a circular shadow. Instead, you get something that looks like this. You would get sort of a dark spot, but it would have sort of yellow. It would have a bright spot, and then you would have these sort of rings of light going out. This diffraction pattern. There was a picture in your book. If you don't have it, you can see it on the screen, guys. But this is called circular diffraction, or diffraction by a circular aperture. I'm just going to show you a picture and ask you what it's caused by. It's caused by light diffraction on a circular object. All right. That's a lot to throw at you. Those both chapters. That's a lot of material. But that's everything that's on the test. Let me just double check this. Y'all think about questions you might have. Yeah, I think that's it. Like I said, there are 27 questions. I try to not put too many calculation problems on it, but between the double slit, single slit, the diffraction gratings, and then the lens and mirror gratings, there's probably, gosh, 7 or 8 calculation problems. You know, those lens and mirror problems, they can be really easy if you know sort of what's going on. But if you're not thinking about what they are, they can take a while if you're sort of stumbling through the numbers. So it's not just knowing how to use the equation, it's knowing what types of lenses and mirrors produce what types of images. In fact, if you know that, you can often pick out the right answer without even calculating. If you know what the image is supposed to look like, what the sign of its image distance magnification are, you can often pick out the right answer without even calculating. All right. Any particular questions or topics you want to go over? Yeah, sure. Like you want to see, like, look at some of the old test questions you made, or?
Yeah, like, if there's one where, like, person one sees an object here, whereas person two sees the same object.
Oh, like in the flat mirrors?
Yeah.
There's no flat mirrors at all in this test. Is that what you're talking about, like when they have the 5 stones and stuff?
Yeah.
Yeah, don't worry about it. The flat mirrors, nothing on this test with flat mirrors. Let's look at some old tests though, and like we'll just sort of thumb through them, and then you holler out if you see anything. I think exam 3 of spring 12 was a good. I might have even made a copy of this for y'all. Oh, there we go. All right, so here's one where some of the rays are drawn incorrectly. This is, you have this one, Jada? The spring 2012 exam? Yeah, so on this one, this first one is okay. This one looks just fine. The second one is not okay. So this one is not correct, but this one is correct. If it goes parallel to the axis, it's supposed to go through the focal point, not through the center of curvature. You just have to know your ray diagrams for these. Let's see if there's also one of those. I said none like this. There's a double lens. You will have one of those. Here's one. You look in a mirror and see an image of your nose that is bigger than your actual nose. Which of these options gives the correct type of mirror? If the image is bigger, it has to be a concave mirror. So the answer is B. It has to be concave. Just knowing those images will help you. All right, those images I sketched out for you. You need to know those really well. Okay, so I would spend a lot of time. I would like paste that up on your bathroom mirror or whatever and look at it for the next few days. There's some stuff here about aberrations. Number 10 here. What's the purpose of the aperture is to eliminate spherical aberration. So know those aberrations. What causes them? How do you change them? Again, nothing like this. Number 11. Aberrations that occur in mirrors. Those are only spherical. Remember, they don't have chromatic aberrations because there's no refraction. Yellow cam, the 2 lens problem. Yeah. It'll be very similar to this. Different numbers, of course, but basically the same. Here's a good one. Oh yeah, we did this one last time. Here's some waves. You'll have a similar question to this. These two waves are out of phase, and you need to know by how much are they out of phase. They're out of phase by a half a wavelength. They're also out of phase by 180, so those are equivalent statements. If they were a quarter wavelength, here they're out of phase, as I said, by a half a wavelength. A full wavelength is this distance, so this is a half a wavelength. If they were a quarter wavelength out of phase, they would be out of phase by 90 degrees, not 180. So half wavelength is 180, quarter wavelength is 90 degrees. You'll have a couple questions like that. This is like that problem I worked before. I have these two coherent waves. They have a wavelength of 4 meters. The first travels 3 meters. The second travels 11 meters. 11 minus 3 is equal to 8 meters. All right, that means they have a path length difference of 2 wavelengths because the wavelength is 4 meters. 8 is twice times 4. That means I will have constructive interference, which will occur because I'm out of phase by 2 wavelengths. If it were a half wavelength or something in between, 2 and 3 or whatever, or some fraction of wavelength, you'd have destructive interference. Here's one where you have to find the adjacent slits, the distance between the slits. I would just say 1 over 540. This is equal to whatever it is in millimeters, and then you need to convert it to meters by moving that decimal place over 3 spots. All right, here's a good one. Laser beam. You'll have something like all of these. So working through these old exams will be good for you for good practice. You need to identify what the various things are. D is 0.1 times 10 to the minus 3. Be careful of your units. Those values will not be given in meters. They'll be given either in centimeters or millimeters. So make sure that you can do those conversions. Here, 650 times 10 to the minus 9 meters. And I want to know the second fringe, that's m equal 2. This is lambda. I would first say d sine theta equals m lambda. I know I use this because I have a double slit. Listen, you need to print out that equation sheet and make sure you go through it as you're studying and just make sure you know which equation goes for what, because that's not labeled there. They're listed in order: double slit, single slit, diffraction, grating. But just make sure that you're aware of what they are for each of them. So here, this is double slit, so d sine theta equals m lambda. So I'd say I'd solve this for theta. And whatever I find that to be, my angle theta, then to find the distance to from the central maximum to the second bright fringe, that means I want to know this distance. We call that y. Remember, that's equal to y equal L tan theta. So you take this angle theta that you found and plug it in there to find y. And L was given. This is L. All right. Once you know how to do it, they're easy, but that's true for all of them. If you know how to do it, they're easy. So, but there are several steps that you have to take. Y'all can do this. All right. Can I clear this? There's one of those problems I was telling you about. If you change one thing, what happens to the others? So for example, here, d sine theta equals m lambda. And y equal L tan theta. If what am I doing? oh, D is being doubled, so I get a factor of 2 there. That means that this sine theta term has to go down by a factor of a half. That means that over here I get a factor of a half, which means that my distance between the fringes is decreased by a factor of a half. So C is the right answer there. You'll have some similar questions. Right, there are all sorts of variations you can do. What happens if you increase D? What happens if you increase lambda? All that business. See, this is just talking about the path length difference. This is our path length difference. That distance is a little extra bit that it travels. This is a diffraction grating. It's very similar. It's basically identical to the double slit. But don't forget that you have to take care of this. You have to say D is equal to 1 over 10,000 centimeters to find it. And this one, the highest order, remember that's when theta is equal to 90. So you say D sine theta equals m lambda, and you solve that for m, but let this equal 1. Alright, so the highest order present here would be 1,000 over 500, which would be 2. There'd be 2 orders present. Anything stand out to you? Want to revisit? That's all the material, but as you know, practice helps on the exam, so practice as much as you can. What else?